I was planning to make a video segment on the use of sensors, as you can see here, when you do finite element calculations in Catia. What I'm going to do is to create two segments. One of them is going to be dealing with, if you go to Censor here, right click. One of them is going to be dealing with applied load sensor and reaction sensor. That's the one that's currently being done. And then a second video segment on create local sensor, okay, which is right here. It's right now. It's dimmed. All right. The problem that I'm going to do is very simple, just so that we can explain what is going on. We have a shaft here at the left end. It is clamped, and at the right end you have a pressure. I have applied the pressure here, and the magnitude of that pressure is 1,000 pounds over this area. The radius of this cross section is 1, so it's 1,000 divided by pi r squared, which is around 300, I don't know, 330 psi. But the point is that the total load is 1,000 on that, what we are applying as a pressure. And then there's a little indentation way here on the top, and I'm going to apply 1,000 pound force on this little square face over there. The length of this shaft is 10 inches. The radius of the cross section is 1. And let's see now. I think I already have some sensors which were created here, so I'm going to delete these, okay? Because I'm going to explain what happens from the beginning. Now, what do we have? We have this is meshed with linear elements, linear tetrahedral elements. In fact, you can see it. It's a very coarse mesh. As a matter of fact, if you look at this little piece here, there is the face that you can see. This face is consisting of 4 nodes. This is important because you will see that 1,000 pounds divided by 4 nodes is going to be 250, which is program imposes on these 4 nodes. Okay, 1,000 pounds divided by 4 nodes. Each node will carry 250, and so this number will come up. Okay, so let's run this thing first of all. The element is linear. Okay, so it's going to be a quick run, and it's done. Okay, so let me deactivate the mesh because we're going to be doing a little bit of operations here. All right. Now, the program ran. I can plot the stresses, the displacement, and everything. But I go to the sensor, right-click, and we go to create reaction set, create resultant sensor. So, as I said, we're going to be discussing the first and the last one. The second one is obscure. I don't use it, and in fact, the first one is also obscure, but at least I can explain it in a reasonable way. So, reaction sensor. You click on it. What it's expecting you is to select a point or a feature or a restraint, something that restrains. For example, maybe a clamp is preventing complete movement of the node. Or even if I have a user-defined restraint, where restraint was the restraint was defined in one direction, displacement was defined in one direction, you can select that. But here, of course, these are all load, or there are no enforced displacement, so all I can do is to select this clamp at the end. Okay, and then you say update. So these numbers appear. Let's make sure we understand what these things are. First of all, forces. The forces tab. Forces tab is, this is the reaction. We applied 1,000 pounds in the positive x direction, right up there, and therefore reaction is minus 1,000 pounds. We applied the pressure of almost 1,000 pounds over that area, which is pi 3.14, and if you divide it, if you multiply Yeah, so I took 1000 divided by 3.14, which is not exactly that area. So you get almost minus 1,000, almost minus 1,000 right here. Okay, the discrepancy is because I'm using 3.145 instead of the actual value of pi. And then there's no force in the z. There's no force in the z direction, and therefore we get almost zero here. This is almost zero. Remember, it's multiplied by 10 to the minus 7. Now, if you go to the moments tab, for example, moment in the x direction. Now, x direction is this way, okay, and there is very little moment there. This is a numerical round off, and the fact that there's if there is any, because of the discretization, there is a moment about x is very small. Notice that, for example, the pressure gives you a force, does not have any moment about x-axis, and this force is parallel to the x-axis, and therefore it doesn't have any moment. This is in principle 0. Moment about y. Okay, so moment about this force creates a moment about y. It's 1,000 pounds multiplied by the radius. By the radius of the cross section is going to be almost 1,000 pound inch, which is right there. And then moment about z, this also has a moment about z. It's that force of 1,000 pound multiplied by the moment arm, which is 10 inches. The length of this shaft is 10 inches, and you get almost 10,000. So we can make sense of reaction. That's not hard. All right, and there we are. Now, let us go ahead and create a resultant sensor, but this is applied load sensor. Applied load sensor, not reactions, applied load section. So it's expecting you to pick something. For example, I am going to pick this face right there, this little square face. Okay, and then we say update result. Let's make sense of these things. First of all, on that face, it says, what is the applied force? Well, I applied 1,000 pounds. No problem. Right there, you can see that. Force in the y direction. It says, wait a minute, I didn't apply any force in the y direction. However, remember that on this circular face, there is a pressure acting. This pressure, based on the finite element load distribution, is going to turn into nodal forces. So there's going to be a nodal force at this point, at this corner point, and the corner point down here. And when you add those up, based on 1,000 pounds that we applied on this face, you're going to get almost 4.5 inches, which is basically very tiny. Okay. And then, of course, force in the z direction is 0, as we expect. There's nothing in the z direction acting on that face. If you look at the moment, let's make sense out of these things. First of all, this moment about y, well, it's on that face, we have a force applied, 1,000 pounds, and the moment about y is that 1,000 times that radius, the radius of circle, which is almost 1,000. Moment about z, on that face, we applied the load of 1,000 pounds. Moment r about z-axis is 10 inches, so you get again almost 10,000 pounds each. Moment about x, well, again, there is a tiny little, because we got a tiny little force here, that this thing, see that? This multiplied by the radius is going to give you almost that thing about the x-axis. So you can make sense out of that. All right. Now let me select a different face. So where is that? Sensor, right click, resultant sensor, applied load sensor. This time I'm going to select this. How about selecting this back face, for example, and then say update. Let's make sure we can interpret this. First of all, on that back face, the only forces that come from the x direction is 250 here, 250 here, which comes from the face perpendicular to it, and that gives you 500. And the moment about x, so let me see now. This is on that face. There were forces, of course. Yeah, you can see that 500. However, it's parallel to the x-axis, so the moment is 0. Okay. Moment about y. Now y is those two forces the 500 pounds that we got, these 500 pounds that we got, has a moment about the y-axis, which is the radius here. The radius of this is going to give you almost 500 poundage. Okay, and you can also get the moment about z. It's remember 500 pound in this direction, 250, 250, multiplied by the moment arm, it's going to give you almost 5,000 pound-inch. All right, let's do another one. Another sensor. Resultant sensor, applied load sensor. This time I'm going to take the circular face. Update. Let's make sure we can make sense out of these. All right. First, forces in the x direction. X direction is pointing this way. There is 250 here, 250 here. That gives you 500. Forces in the y is going to give you the total area of this times the pressure, and it's going to give you almost 1,000 pounds. And force about z, force about z, almost 0. This is 10 to the minus 7. And you can take the appropriate moment arm and the forces that we just discussed about, and you get these numbers. For example, if you look at the moment about z, this force, 550, 250, 250, that is force in the x direction, 500 times the moment arm. Moment arm is 10 inches. You get 5,000 inches. Now I don't use these load sensors, applied load sensors, but I suppose one can use it too. Reaction is more useful to me. Now, one last thing is that you can create a global sensor. Global sensors are also kind of useless because, well, it gives you strain energy in joules, it gives you the maximum displacement and maximum von Mises stress, etc., which can always be obtained by looking at the contour legend, which is on the right side. But anyway, for example, if you want the maximum von Mises stress, you say okay, and there is going to be double click on it. You're going to get the maximum von Mises stress is that many psi. Well, that's a huge number. Okay, but keep in mind that you got to be very careful in accepting this as the true value, because you don't know where this is happening. It could be that it's happening at a place where you have, some discontinuity here, which was created just because of the way we had to model this problem. As a matter of fact, if you say where's the maximum stress, let me see. For example, first of all, let's look at the von Mises stress. Okay, there is the almost. Let me change the rendering here. Okay, yeah, right there. You see this? It's happening right there because you're applying a load somehow. Now this is an approximation, and approximation of how you apply this kind of a load, and it may not be realistic. Anyway, this may not be a critical area for you. You've got to be very careful in using this. So I think I'm going to stop here, and then we will do the video segment, the second video segment on a different example, which is dealing with let me see, dealing with local sensor. Okay.